Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day in my virtual classroom. I haven't done one of these kinds of videos before in a while. This is a solution guide video to a textbook assignment for my integrated Math 2 class. I think I'm going to be following up a little later today with an integrated Math 1 solution guide. I don't need my headphones anymore. I just came from teaching. My integrated Math 1, put it down on the ground. I'll be doing my Integrated Math 1 solution guide video again later today as well. This one here, we're starting geometry stuff, so we're looking into things regarding angles and their relationships. We're not yet getting into the parallel lines bits, but right now we're talking about when two lines intersect, when we see what are called adjacent angles. Excuse me. Well, adjacent angles are one of them, but vertical angles and linear pairs. Alongside them, we'll see complementary angles, supplementary angles, and overall adjacent angles. So some of those words I just said are things that you're going to kind of have assumed to have seen definition-wise, or you know some semblance of them, but I'll help tackle them with you when it comes to the kinds of problems that are asked with them, as well as the visuals that tie in with them. So once again, some words that you may want to know going into this as a refresher or an understanding of, even though this is specifically about vertical angles and linear pairs, are vertical angles, linear pairs, complementary and supplementary angles, adjacent angles, acute angles, right angles, obtuse angles, and straight angles. Those are all different bits of terminology angle-wise that you might want to know something about when it comes to this particular video. The reason why I'm shortening you on that is because I'm looking at my time, in about 22 minutes here from now, I got to do a meeting. So this is going to be a relatively fast video. I'm actually only going to do problems from the problem set that I assigned to my class. So they'll be circled. You'll see them. Sorry if I skip out on certain questions that you may otherwise have. But if you do have a question, please leave it in the comment section down below in the description section on YouTube. Sorry. See the description section on YouTube for timestamps to certain problems if you'd like to, I suppose. I don't know if I'll put them up, but go to the comment section down below. Anyway, I'm wasting my time here because I'm literally running out of time. Let's go ahead and get started on the problem set. So, okay, here we have a diagram, and before I do anything with the answers in number one and such, let's start marking up some things that may be important to us. I'm going to save this part for when we hit numbers 2, 3, and 4. I'm going to save the 50-degree part. That is irrelevant at this very moment for number one. But number one is important to see that points B, F, and D are collinear, and points E, F, and C are collinear. What collinear means is they all fall on a line together. I can draw a line literally through those points. So if I draw a line through there, those 3 points, and I'm doing it really big just to emphasize it, and I draw another line through here, through those 3 points, you can see that there are 2 lines here. This is important for vertical angles and linear pairs. I said you need to make sure you know the definition of vertical angles. Vertical angles are angles that are opposite each other when 2 lines are drawn. These 2 angles that are marked with arcs right here are vertical angles because 2 lines were drawn and these angles are opposite each other. These 2 angles right here opposite each other that are marked in green, the double marked, are also vertical angles. Notice that this A, you got to ignore this ray from F to A right here completely. Completely block it out if you can and just look at the entire angle made right there. This is a vertical angle pair. This is a vertical angle pair. What is true about all vertical angles, it's a theorem, is that all vertical angle pairs are congruent to one another. So these 2 are congruent. That means they have the same angle measure. These 2 are congruent. They have the same angle measure. That is always true of all vertical angles. It's a natural occurrence when you have 2 lines that go together. And I'm really specifying the line stuff because let me show you what's not a vertical angle pair right here. You might think that right here, even though they're marked, even though they're congruent, that's just a coincidence here, but these are not vertical angles right here. These are not opposite. They may appear somewhat opposite each other, but they are not opposite each other from 2 lines that are drawn. Yes, this is a line, but this is not a line. That is a bend of 2 different rays. These are not vertical angles. Here's another example, not regarding this stuff here. Well, sort of here. These are also not vertical angles right here. This is a line, sure. This is not a line. So even though they're opposite each other, it's not opposite each other when 2 lines are drawn. And that's the big specific difference. And I know I'm spending a little time talking about that, but that is really what this talks about, vertical angles versus linear pairs. I will ask, are they opposite each other when 2 lines are drawn, yes or no? Now the linear pair stuff, going back to this big ol' thing here, linear pairs are two adjacent angles that form to make a straight angle. So this angle here and this angle here, when formed together, that angle here and that angle here, when formed together, make the entire straight angle. Basically, a straight angle is a 180-degree line, like that. So when formed together, these two make what's called a linear pair. They have to be adjacent. They have to be neighboring each other. Common side, common vertex. So that's a linear pair here. Again, this is why these lines are important here. That's a linear pair. This is a linear pair. This is a linear pair. And I'm circling the angle mark, so hopefully you're seeing the entire thing for what it is. Those two divided by that. And this is a linear pair. Wait, did I cover them all? This is a linear pair. This is a linear. There are 4 linear pairs when it comes to that set. All linear pairs. No other linear pairs are made with these things because there are no other 2 lines that are drawn in this whole ordeal. There are some linear trios, maybe. We'll run into some of those, but that's the crux of it. All right, that being said, let's see if we can answer the questions on number 1, knowing that information. Oh, the other thing you're going to have to know is the name designations for angles themselves. I'm going to be very quick on this. Angle BFC, guys. BFC, find B, draw it to F, draw it to C. See the angle that's made? That's angle BFC. That's how the 3-letter name designation works. Start from a point, go to the vertex point, bend it to the other point on the other arm. There's your angle. So they're talking about angles BFC and DFE. They want to know if these are vertical angles, if these are linear pairs, or neither. Well, we just went over this. 2 lines drawn and these 2 angles are opposite. These are definitely vertical angles there. I am going to move forward, but that's the drawing. That's the idea of it. Some of these I won't even draw on here because I understand if you're doing this as a homework assignment and it's in the textbook, you might not know specifically. You might not be able to draw them and color code them, so I understand that. But let me do a couple more. BFA and DFE. Well, this is one they specifically said were not vertical angles. Listen, they are congruent, but that's a coincidence. They marked them congruent for us. They told us they're the same. They're not opposite. This isn't formed from 2 different lines. Here's a line, and here's a ray, and here's a ray. We need 2 lines that intersect. These are not that. They're also not a linear pair. They're not adjacent. They may share a common vertex. All these angles share the same common vertex, but this angle doesn't share any sides with this angle, and they don't form to make a line in total. This is neither. All right, the next one here, BFC and CFD. BFC and CFD. Okay, here are the 2 angles here. Notice how, definitely not vertical angles, but notice how when drawn together, this ray that divides this entire straight angle means that this is one entire line made from this angle, and they are adjacent to each other. That's an example of a linear pair. This is a linear pair because together, and here's the example. If this was, well, this is 50 degrees. If this is 50 degrees, this is probably answering something before. No, actually, no, we don't know this is 50 degrees, actually. That was, this is 50. If this was 60 degrees here, then this would be 120 degrees because together they add to make 180, right? They add together to make the line. That's the idea of forming the straight angle. Anyway, that one's a linear pair for show. All right. Let's try and do the others without actually drawing things on there. See if these make sense when I do them. AFE and AFC. AFE is right there. AFC is right here. So AFC, AFE. Total, they are adjacent because they share the AF and the F vertex. And they make the straight angle. You really got to ignore this FB ray. This really has nothing to do with it. I'm going to try and hide it as best as I can right here, just boxing it out. Okay, so you see that there? Boom. AFC and AFE. Do you see the straight angle now? That's a linear pair right there. Look, you can't do this either, what I just did boxing it out. You're going to have to perceptually do that the best you can. That's another linear pair. All right, part E. BFE and CFD. BFE is this big obtuse angle right here. It looks to be more than 90 at least. And CFD. BFE and CFD. Okay, that's the one. So that's this whole thing with this whole thing here. Notice how they are formed. They're opposite angles formed by 2 lines. The line BD and the line CE right there. Those are vertical angles. That was that other set that I had in the past there. And finally, AFE and BFC. AFE is right here. BFC is right here. They are not opposite each other formed by two lines, and they are not adjacent to each other, and they're not supplementary. Therefore, they are not a linear pair. They're not vertical angles. There's no specific relationship among this one, between this one and this one. That is a neither case. That is a neither case. Now, why were these things important? Because identifying when you have vertical angles versus linear pairs here will allow you to determine more information on these graphs if necessary. Case in point, the next questions, numbers 2, 3, and 4, we have to find the measures of certain angles, only knowing small bits of information about being aware that 50 degrees appears in a couple angles. Let me kind of recapture this diagram here. Sorry that you're going to get a little letter involved as well. But I'm going to paste this diagram right here. Boom, nice and big. And I'm going to add some of that information back in. So we have 50 degrees here. They tell us up above it's 50 degrees. And this is 50 degrees. As you can see the arc marks, they're kind of telling you these are congruent. So 50 and 50 right here. And we got to find some other missing angle measures. And I plan on doing that right now. All right, find the measure of angle AFE. So we got to find this guy right here, AFE. Now this one's a little interesting because despite me talking about linear pairs and vertical angles, AFE is not a linear pair with anything except for, well, I mean it is, but it's a linear pair with this, but we don't know what angle BFC is either. What I do see here, if you can notice this with me, guys, look at this whole line, BD. It's also known as a straight angle, BFD. That this whole thing is 180 degrees. The combination of all three of these together is 180. This 50, this unknown, and this 50. So I could do something like this. I could say if I had 50 degrees with the unknown measure of angle AFE and the other 50 degrees, total that's a linear trio that adds to 180. It's not a linear pair. That doesn't mean that they don't add to 180. 50 plus 50 is 100. And just like algebra, measure of angle AFE might as well also be called x. To solve for x, we got to subtract 100 from both sides. So the measure of angle AFE equals 80 degrees when you subtract there. And that's the measure. And you know what? When you get your measure, it's good to write it in because you might use that number for something later. Maybe the next, I don't know, maybe the next problem here. All right, let's look at the next problem. Find the measure of angle DFC. So DFC is this big guy right here. And you know what? I think this 80 will be nice to use. There's more than one way you can do this problem. I want to make sure you guys know this. The two ways I'm thinking of, and I'm only going to do one of them, but the two ways I'm thinking of is, I don't know if you notice here, we just talked about it, but DFC is a vertical angle with BFE, and BFE is this 50 plus this 80 right here, right? This is a vertical angle with it, and all vertical angles are congruent. You know what 50 plus 80 is? 130. Therefore, DFC is also 130. So you could do that. If you don't recognize that, though, let's go with a linear pair sense instead. Let's talk about this 50 degrees. This total is a linear pair, that and that. So this 50 degrees with the measure of angle DFC adds to 180. Okay, and then we subtract 50 from both sides, and we get the measure of angle DFC equals 130 degrees. So notice there, we still get 130 regardless whether I added 50 with 80 and said they're equal or did it this way. And the final one is measure of angle BFC. Hang on, this is 130. Final one is measure of angle BFC right there. You have several options. We can say it's a linear pair with the 130. And then you do 180 minus 130 is 50. So notice we did 180 minus 50 to get 130. And then we did 180 minus 130 to get 50. That's one of the reasons, and that's part of the proof as to why vertical angles are always congruent. Because you have two different linear pairs with the same angle. Therefore, these have to be the same measure. So the other way to talk about it, of course, is as two lines have opposite angles here, these will be congruent. If this is 50 degrees, this is 50 degrees. The measure of angle BFC is equal to the measure of angle DFE. And the measure of angle DFE equals 50 degrees. Therefore, because they're vertical angles, but therefore the measure of angle BFC equals the picture of my face. BFC equals 50 degrees. Notice I'm putting measure of. That's an important syntactical thing for geometry. All right, I'm going to skip number 5, and I know that time is pushing against me here. I have 11 minutes left, so let's go. Number 6. Oh, here we go. Determine whether each statement is true or false. If false, explain why. All right, I'm probably going to type some things here. Number 6. If an angle is acute, that means less than 90 degrees, then the measure of its complement must be greater than the measure of its supplement. Okay. All right, I have some unknown angle. I have some x. We know that it's less than 90 degrees. In fact, it's between 0 and 90 degrees here. If it's acute, the measure of its complement. So two complementary angles are two angles that add to 90. So some unknown x's complement would be 90 minus that thing right here, 90 minus x. Because, think of 60 and 30. If some angle is 30, its complement is 90 minus 30, which is 60, because 30 plus 60 is 90. Its supplement would be 180 minus x in terms of two angles that add to 180 degrees is that. So let's see. If an angle is acute, the measure of its complement must be greater than the measure of its supplement. Well, what they're telling us, guys, is that 90 minus x, however many degrees that is, that's going to be greater than 180 minus x. That doesn't sound right. We're subtracting the same angle. Heck, let's solve this algebraically. Add x to both sides. What happens is the x's canceled. I guess that's okay. But you get a statement that says 90 is greater than 180. Huh? That doesn't seem to work. No. An angle's complement will never be greater than an angle's supplement, and if an angle's obtuse, then it doesn't have a complement. So this is never true. This would be a true statement. This would be a true statement if they did this the other way. If they said the measure of its supplement is greater than the measure of its complement, that would always be true if an angle's acute. So false for this reason, for the reason that you see right here, but also I'll just say complement, supplement should switch. If you wanted to make it a true statement, they should switch. Okay, number 7. A pair of vertical angles may also form a linear pair. Well, a pair of vertical angles, by definition, means that when two lines are drawn, we're looking at the angles opposite each other. It's possible for a pair of vertical angles to add to 180 degrees, but they're not saying supplementary. They're saying form a linear pair. Linear pairs, by definition, have to be adjacent to each other. Vertical angles are never adjacent to each other because they never share a common side. They share a common vertex, but a linear pair shares a common side here. These will never do that. This one is also false. This would be true if they said may also be supplementary. It's possible for the vertical angles to be 90 and 90. Vertical angles, a pair of vertical angles, however, may be supplementary. Okay. It's possible for them to be supplementary, and linear pairs are supplementary, but to be a linear pair, they have to be adjacent. That's strictly vertical angles cannot be. But if they were both 90 degrees, they would add to 180. All right, number 8. If two angles are supplementary and congruent, the measure of each angle is 90 degrees. If two angles are supplementary and congruent. Okay, so we're saying this. Let's say I have some unknown angle x, and I add some unknown angle y, and I get 180. They're telling me they're supplementary. They're also telling me they're congruent. So you know what that means? Their measures are equal. I'm doing the system of equations style. X equals y. You know what I'm going to do? If x equals y, I'm going to take x and substitute it in for that y right there. If you guys know anything about algebra, you know you can do the substitution in a system. So now I have an equation that says x plus x equals 180. And that means 2x equals 180. Divided by 2, that means x equals 90. X equals 90, y equals 90, right? If x equals y, therefore then y equals 90. Okay, what are they stating? If they're supplementary and congruent, the measure of each angle is 90 degrees? Yup, true. There are other ways you can do that clearly. You can draw them. You can draw a linear pair that's supplementary and put them equal to each other. The only way to make those two angles equal to each other is if that goes, it bisects it right down the middle like that, and that means we have a 90 and a 90. There are a lot of ways you can do it. You don't even have to necessarily do it. They don't say show work. I'm giving you the validation behind the statement that it's true. I'm going to skip number 9. I'm going to keep moving forward. All right. Next ones. You can represent the measures of an angle and its complement as x degrees and 90 minus x. So I already mentioned this. If some unknown angle is x, its complement is 90 minus x. If some unknown angle is x, then its supplement is 180 minus x. We can use these expressions to help us here. Let's find the measure of some unknown angle x, given that it is 3 times the measure of its supplement. So the supplement's 180 minus x. They're telling us that x is 3 times the amount of 180 minus x. They're not equal. Do I put the 3 here and say it's 3 times if I have to triple the x? No, they're saying the x is 3 times that amount. That means I'd have to triple the supplement to match this thing here. This thing is 3 times bigger, right? Check this out. 18 is 3 times 6. 18 is 3 times bigger than 6. I don't do 3 times 18. I do 3 times 6 to make them equal. Okay, So I solved, sorry, I'm going fast. I have 5 minutes and I probably have to pause and resume this later. So I distribute here. I get x equals 540 minus 3x. I can add 3x to both sides. I get 4x equals 540. And I divide by 4. I don't know that off the top of my head. I get x equals 1. Is that a clean number? I hope I did this right. 3 times the measure of its supplement. 540 by 4. What is that? 140 divided by 4, 35. 135? 135. I should have gotten that a lot faster than I did. So that's the original angle. You can double check that with the supplement. You'll get the supplement's 45 degrees if you do 180 minus 135, and 135 is 3 times larger than 45. Okay, number 11. The measure of the supplement of an angle is 3 times the measure of its complement. So we have some unknown angle x, but we're comparing the supplement of that angle to its complement. The same thing is involved with the 3 times portion. The supplement is 3 times larger, therefore we have to triple the complement in order to match it. And notice they still want us to find the original unknown angle measure comparing the complement to supplement. By distribution, we can determine here that 180 minus x equals 270 minus 3x. If I add 3x to both sides here, negative x plus 3x is positive 2x. If I subtract 180 from both sides, 270 minus 180 is 90. I get 2x equals 90, divided by 2, I get x equals 45. The original angle is 45 degrees. Its supplement would have been 135, and that's 3 times larger than the complement, which would have been 45, just like the last ones. Only now it was supplement and complement, and there's the new angle. All right, number 12. The measure of an angle is increased by 20, the measure of an angle increased by 20 degrees is equal to the measure of its complement. Some unknown angle, its complement. They're saying, let's go ahead and increase the original angle, and then that will be equal to the complement value. So that's the setup. Original angle increased by 20 will equal the complement value. You could do guess and check, but of course the whole goal is, can you set these up and solve algebraically? Because we can make these really tricky. I remember seeing I gotta find it. I'll find it for you at some point, and I'll make it a challenge question and say, here's what you do. There's a lot of distribution and parentheses and grouping. It's just a lot of stuff there you do to solve. Anyway, add x to both sides, divide both sides by 20, you get 2x equals 70, divide by 2, you get x equals 35 degrees. Apparently, there's some original angle 35 degrees that if I increased it by 20 to make 55, that would be its complement. And that makes sense. 35 plus 55 is 90. So those do seem to work out. Okay, I have one more question here. I'm going to move on down to it. It's this number 18. If one angle of a linear pair is acute, then the other angle must be obtuse. Explain why. Okay, an acute angle is less than 90 degrees. And an obtuse angle is between 90 and 180. Now they're telling us explain why when you have a linear pair that happens. I'm going to first give the visual and I'll see if I can type it out. So a linear pair is made from any two adjacent angles here when then divided by an array such as this. This could be the linear pair with these two angles, or this could be the linear pair, this could be the linear pair, and this could be the linear pair, two right angles, but they specifically say if one angle is acute. Basically, neither of them can't be right angles. So even this is acute, and if you see, once one becomes acute, the other has to become obtuse. Why? Besides the drawing, mathematically, why is this true? Because they have to add to 180. They have to add to 180. Let me actually do this in terms, let me call this x and change this into a y. Change this into a y right there. The reason why one has to be less, or when one's less, that the other has to be in between here, is because they have to add to 180. And when you do 180 minus a number less than 90, then you're going to get a number that's more than 90. So 180, and this is not a good way to write this math-wise, but 180 minus a number that's less than 90 has to equal a number that's more than 90 degrees. And by definition, acute is less than 90, obtuse is more than 90. So that's me saying it out loud. Unfortunately, I don't have time to type it. I have to go here. But that ought to do it for this one, guys. I sure hope the solution guide video really did help you with just the general explanation on what's happening there. If you have any other questions, again, leave it in the comment section down below. I appreciate it. Sorry, I got to go. I got a meeting. Thank you. Take care.